Okay, so I've been talking about probabilistic programming for a while now, and we have been talking about inference, but we have not really said anything about inference, about the practicalities of how you would do this. Not only how you would go about this, but also what is the value in doing this. And so today, what I want to do is walk through a certain example that is a very simple one, but that hopefully highlights like why probabilistic programming is cool and why you can actually learn things from or actually fit models to observe data and how that could be used when you see some observed data and build some model for it. The purpose of this tutorial is to give you a demonstration, but also allow you some hands-on code, like give you some hands-on code so you can play around with it. And also, it's a bit complicated to expect someone to jump into probabilistic programming without any basics of what inference is and why we use inference. So hopefully this gives you some context to get started. So to start off with, um, let's say I want to write a function to generate a bunch of coin flips. A fairly straightforward task. So, for example, the result of a flip um, um, with a certain probability, or let's say, uh, uh, I want, let's say, I want to start by writing a function that takes in number of flips and outputs number of flips and output a series of outcomes. Can someone tell me how I might go about representing coin flips in code?
So like you will have states, right? So like let's say as you keep on encountering a particular state, you will increment the count of that state, right? The like number of times it has occurred. So let's say if you're talking about coin flips, there are two states, right? Head and tail.
Mhm.
And as you keep on like let's say rolling out dice, right? So suppose you have so at each observation you will see whether it's head or tail based on some like um randomness value, right?
Uh,
And if it's let's say about that threshold, then you increment let's say for heads. If it's below, then you let's say increment for tails, right? Something like that. If that
so
so
you're saying, I think
like a Monte Carlo simulation.
the word you're looking for is sample, a random number,
Yeah. Okay. Yeah.
and then you mentioned thresholded.
Yeah.
If above,
Then maybe increment for let's say head
then
and yeah,
heads. If below,
then tails.
then tails.
Like if above like so one would be like including that bound as well, right? So if
Right.
greater and above, so like something like that.
And let's say tails. Cool. Now can you think of how I might represent a coin flip using statistics? And that's a very bad question to ask someone.
Could you
Uh,
like give like more details about like in statistics, like how do you
right.
like
So
mean?
I think improve my question. So if I say the outcome of a coin flip is this random variable x, uh, and this is now I'm walking you through the process of how like say a scientist is going to write this up or a mathematician is going to approach this problem. The English stuff we all understand. Like, okay, sure, you're going to observe heads or tails. So you start off, and the coding stuff, most of you will understand because you've been working on this stuff, so you understand what sampling a random number looks like. Um, but then, like implementing this as a mathematical function is the task that where you lose out most of the people. Like they will get stuck. Which is again why like we're walking through this from end to end, starting with a certain experiment where flip a coin. We discussed there is an input. We discussed there is an output. We discussed there are states that a coin can take, which is a finite number of states. And then we go about the algorithm, or let's say pseudocode. Well, no, let's say algorithm. And then now we're getting into the mathematical representation. So if X is a random variable, then can you tell me where I might sample the values of X from?
From some distribution, right?
From some distribution. What could be the potential distributions I could sample the value of X from?
Yeah, it would be Bernoulli, right? Because it's like coin flip 0 or 1. So like,
Okay. Can someone other than Jeff follow up and explain what a Bernoulli distribution does? You can look this up, you can Google this, and you can explain it. I have no issues with that. I just want you to understand what it does. And the question was, for coin flips, you sample from Bernoulli distribution. Can someone just explain what a Bernoulli distribution is? Or could someone explain like what? Yeah, someone.
yeah. So like on a higher level, basically it's a discrete distribution, let's say,
No, hold up, hold up,
where
hold up. I know other people know this answer. I want to push them to answer.
yeah,
No, you know this
okay,
answer. I don't want the answer from you.
okay.
Anyone else?
So if we have two possible outcomes, basically success or failure, so every event will be represented by a probability P. Say so if we consider of unbiased coin here, then we would consider P equals to half, which means that the probability of getting a heads is 1/2, and then Q would be I think 1 minus P, which is again half, like the remaining value. And the so these probabilities at any point would be represented using P NC R into P raised to R into 1 Q raised to R, right? Q raised to N minus R, I think. If we toss the coin N number of times, then the actual probability of getting a heads.
This is actually quite perfect. I'm just writing all of this up. Does everyone follow this so far? And I don't know if you're not familiar with the Bernoulli distribution, then I should dive into that a bit more, but I want people to speak up and tell me. Also, someone who is not Jay or Deep. I mean, I don't know if people are hesitant or if you
It is
just...
clear to now.
Okay, cool. But like feel free to have it, like this is a call to have a discussion. Like I'm not testing you. In fact, I would be testing myself and my ability of explanation since I stopped teaching last year. But yeah, like it's just to have a discussion, and if you don't know something, that's great. Please let us know so we can teach each other more or less. Cool. So Bernoulli distribution, the thing I've missed out, can someone point out if this is the right way to write this or not?
You also have to specify right number of trials.
You also have to specify
Number of trials, right? How
correct.
many times?
So if I had to write something, then I should not write this like this. If I had to write a distribution, then I would specify this is Bernoulli with a certain probability. So this is the P that I'm talking about. And then because the Bernoulli has only two possible outcomes, therefore this becomes 1 minus P by default. So if there are only two possible outcomes, A and B, which might correspond to heads and tails, so A is equal to heads, B is equal to tails, Then P of A is equal to 0.5 and P of B is equal to 1 minus P of A, which is 0.5. The reason, and I know you know, I assume all of you already know this, and I'm just repeating it because this is important to formalize. Because this is the simplest case of these kinds of probabilities. You can increase the space of outcomes, and then each outcome will have a certain probability. And as that outcome, like someone mentioned before, this is a discrete set of outcomes, in which case it is countable. In a continuous case where you have infinite possible outcomes, or a real numbered, a real valued space over outcomes, or the outcomes are a real valued space, in that case you have a certain distribution over this space, which tells you the probability of each individual point, or to be even more precise, a probability of a set of possible outcomes, because there is no such thing as a probability of an individual event or a continuous probability distribution, which again we will get into a bit later. But for now, a very simple case, coins being flipped, you have a certain probability of obtaining heads, a certain probability of tails. Because we have said this is unbiased, because we have said the coin is unbiased, we have set this probability to be equal, which is, so let's put this on a separate line. If coin is unbiased, then P of A is equal to P of B. And using this equation, we get that both of them are equal to 0.5 because their sum is equal to 1. So each of them must be half of 1. So, so we use two facts and we know sum of all probabilities equal to 1. That gives us P of A is equal to P of B is equal to 0.5. Again, this is fairly straightforward. You all already know this. And so now we get back to the representation of how we want to go about this. So first we specify a distribution and the parameter for that distribution, which in this case is the probability, where we specify P is equal to 0.5. Next, we sample from this distribution. And here we specify the number of samples, which is say 10 samples. And this is my set of outcomes X, where I have sampled from a certain distribution. So hopefully this syntax makes it clear like what a distribution is and what samples from a distribution are. So yeah. So in a sense, what you're doing is you're saying, I want to flip a coin 10 times, where each time this is the distribution that I'm sampling from. So each time I have half or 50% chance of heads and 50% chance of tails. And the reason we call this IID is because these are independently drawn samples. There is no chance of one sample influencing another sample, because in a sense what you can think of is you create 10 parallel threads and you draw sample from all of them simultaneously. You're not doing that here, but you could do that here, which is what the point of IID samples is. Instead, if I was doing something like, could someone tell me how I could draw non-IID samples? Or I don't know if that's too hard a question, but so if these samples are independent, could you like add say 3 lines of code and tell me how I could break this independence?
So here, if the threshold is 0.5, right, because it's equal. So if we insert some sort of condition that the probability should always be greater than 0.6, then it could be non-IID, right? Because everything would then be heads.
So, okay, so this is a great point to add a lesson. So let's first code up what Deep said. you said b is equal to 0.6, and if I sample from this, then your claim is this is non-IID. Am I correct?
So what I meant was that you make a distribution with p equal to 0.5 and only sample the values above or below us below the threshold. So like you give a condition that you keep on sampling, and the only values that you'll consider will be like above 0.7 or something like that. So you try to bias the sample.
So by default, I draw one sample. And now you're saying if I add a condition, if xi is less than, and so a Bernoulli distribution gives you zeros and ones. We correspond these to heads and tails, but it gives you numbers as an output, not heads and tails. So if I have numbers, if xi is a number and I say xi is less than 0.5, which is either 0 or 1. So I'm just, I could just as well write xi is equal to 0. It's the same thing. If xi is 0, then I want to ignore it. So what I'm doing is while xi is 0, I draw the sample again. And until I get a 1, I keep redrawing that sample. Is that what you're saying, Deep?
Yeah, sort of.
So this is correct. This breaks independence because each next sample depends in a sense on the previous sample. If the previous sample is 0, then the next sample will be redrawn. Then that sample will be redrawn. And if the previous sample is not 0, then the next sample is not redrawn. I was going to explain IID in a sort of different sense where you create a dependency between samples, but I guess this is also breaking independence because your samples are no longer drawn independently. So yeah, I guess good example. But the only point I was trying to go for is like there are ways that you might be breaking independence when you're drawing these samples. So be careful about when you think your data is IID and when it is not. I will pause here for questions.
But like if let's say particularly if you're using like a bias coin, then also like the samples would be non-ID, right?
So originally I thought that's what Deep was saying, and that's a good question. I give me 1 second.
Yeah.
Yeah, sorry. Weird message. Anyway, what I was so originally, if this is what you were doing, um, if you're saying this is 0.6, then your x, and you do the same thing for x, your samples are still IID, are still IID in the sense that they are independent and identically distributed. Where does the independence come in from? Independence comes in from this parallelism possible. If parallelism is possible, then you're doing each thing separately. which means they are independent. What this does is it tells you that the coin is now biased because one outcome is more likely than the other. Do you follow?
Yeah.
So that removes your unbiasedness, but it still keeps your data IID.
Okay. Got it.
So yeah, like this is just the technical way that I think about it. If parallelism is possible, they are independent. And if they're drawn from the same distribution, they are identical. So can someone give me an example of breaking this identical part? So we've seen failure of case one, biasedness fails or unbiasedness fails. We've seen case three, which is, or case two, which is what are we doing? This is no longer from an identical this is no longer independent. Can someone give me a case for non-identically drawn data?
So like if we change coins with different amount of biasness. So like two different distributions, I'll take one half from the first coin and the other half from the second coin, the samples.
So if I define B is equal to Bernoulli, now I define a B1 is equal to Bernoulli 0.7 or 0.6, whatever. The bottom line being, as long as I have for I in range 10 or n samples, xi is equal to a simpler way to write this. Right. And yi b1 dot sample. So I do this for range 5 n by 2, and then I combine x is equal to xi extend yi. So I'm basically drawing samples from two distributions. So all xi's are sampled from the same distribution, so they are IID. All yi's are sampled from same distribution, different from xi, but all yi's are IID. But by combining xi's and yi's to create my random variable x, I'm creating non-IID data because non-identical, they're drawn from different distributions, so they are non-identical by definition. Okay, so we've gone through three cases of like where IID data might not actually be present. So, and the reason I did this was because typically when you work with problems, you just have a data set in your hand. You just have a data set, which will be like some sort of observations. And you don't know where these observations came from. So you have to actually think about whether these observations are independent and identically distributed or not. And then you have to build a model for this. And by using coin flips, we've created a very simple set of outcomes. But in practice, these outcome spaces may vary very vastly. So you have to understand these failure cases of how these data might actually have been produced and what processes could have produced this data. Then think about, okay, in these processes, do you think there is an independent data generating mechanism or is there some dependency? And thereafter, you can process the data. Now to get to some real code, I'll pause here if anyone has questions. I would encourage you to ask me to repeat things that I haven't been clear on. Oh, I did not see chat before, my bad. I followed Amos with you. Okay, cool. If there are questions, please pause me and make me repeat this. But if not, I'll get into the coding bit. So suppose I want to write a function, and for the purpose of this tutorial, I've already written up a function, so I can just copy it over. Um, so let's say I want to generate a series of coin flips. And I want to write a function that I want to call flipper, where I want to return data, which is basically a set of outcomes, 1, 0, 1, 1, 0, and so on. This is just a representative example. Let's say I don't want to return the exact data, but this is a series of coin flips that corresponds, where 1 corresponds to heads, 0 corresponds to tails. And we've discussed that you can do this using this Bernoulli distribution. So I want to, let's say, from distributions. Yeah. And the way you sample, should actually go for, let's go for Pyro directly. So there is a certain syntax for PyTorch, there is a certain syntax for Pyro, slight differences, but doesn't really matter, and I'll explain why Pyro syntax is important here. So let's say my argument for this function is n, where n is an integer that indicates the number of coin flips. So I take in an argument n and I return data. Now, can someone tell me what I should do first inside?
Initialize your distribution, like with some probability value. I think I have called directly Bernoulli.
My bad. Import Pyro. So now I have dist and I have dist.Bernoulli. And for this dist.Bernoulli, I would have to define a probability. So it's probably better to define a probability here. And we said we want to start with an unbiased coin. I will also need torch because I need to define probability as a torch tensor. Okay, so I have initialized the Bernoulli distribution. Can you tell me what the last thing to do after initializing the distribution is?
Sampling like values out of that distribution in times.
Maybe I need a th.tensor here. I'm not sure, but I think I do.
Think that should work, right? It's
Okay.
normal.
Let us see if flipper of 10 gives us the results we need. We do not have the results. Takes an iterable of int. Oh, cool. Okay. This is for data.sample. Maybe I did not need this. Or maybe I did. It takes an iterable of size n. My bad. It's a bit annoying. I'm sure there's a better way to do this than I showed you, but no, this is takes an iterable of int. Oh, oops. Am I missing something?
I think th.tensor converts it to float.
I see. Yeah, you're right. Then the simple thing to do is let's define some sequential sampling here.
You can, I think, directly pass it, right, using d type as integer in torch tensor. Uh, like whatever the value, and like you can change the d type to int if that's what it's asking. Torch int, whatever, like 32 or 64, like
I think you want to write something like a list comprehension, right? What you are doing is inside b.sample you are passing a tensor directly, which consists of only one element, which is n. So th.tensor you'll have to write outside, I think.
no, right? It's like he's passing that for like how many samples to be done, trials.
I think this was the stupid mistake I made. Yeah.
Okay.
Yeah, it's just syntax stuff. It expects a certain size. Size is an iterable in torch. Therefore, it works. I think the keyword argument for this, in case you want to know, is also size, or is it shape? Nope, probably also not shape. What was the argument? I don't remember, but the default argument is this. So as you can see, we have a certain data set that is, or let's call them observations. So our observations are 10 coin flips. And if you want to check observations.shape, shape is 10, 1. Cool. So far, so good. We've defined a sort of coin flipping process that generates a bunch of data. We can also change the parameterization such that P is now an argument, and then write down P float probability of observing heads. Cool. And let's try this out now. If I change 10 and then I make it 0.9, which is highly likely to see head, oh sorry, highly likely to get heads, then I should have a lot of heads in my data. Again, heads is corresponding to 1, tails is corresponding to 0. I've kept the coin really biased and I see a lot of heads. So yeah, that's basically, this is still Python. This is not really Pyro, because this pyro.distributions, pyro.distributions Bernoulli is just torch.distributions.bernoulli. For example, to illustrate this point, dot import distributions tdist, and suppose I replace this with tdist.bernoulli, it will still do the same things. So I hope you understand, like the way a library is built on top of another library. Really, in this case, it's really just using the other libraries distributions. What Pyro does that is cool is will be shown in a couple of minutes. Anyway, so what I can do is now I can generate a bunch of data on coin flips by biasing that coin. But the real question I want to answer is, suppose we see a data set which is 1 1 1 1 1 1 1 0. The question is, let's make it an even easier question. Suppose I see such a data set what I want to infer, what could or is the coin biased? The first and simplest question. Can someone answer this question for me? This is open to anyone. Suppose you see a data set 1001, 1010. This is a set of 8 coin flips. And the question is the coin biased? If not answer, try to guess and walk me through how you try to guess it.
Oh, we cannot guess it from a sample, right?
We cannot, the question is like accurately or not. So a sample is essentially a set of coin flips. So suppose I tell you this is 1 0 1 0 1 0 1 0. Now do you think your accuracy of guessing will increase or not?
We could define threshold that suppose probability of heads should not be greater than 0.6 or less than 0.4, or similarly for tails. So we could have some probability margin or threshold that if it is less than 0.2, then it raises alarm bells that it could be a possible biased coin.
Okay. So if I had to rephrase what you're saying, or my understanding of what you said is, if we can define a threshold and generate a bunch of data and then compare that to this data, is that what you're saying?
The question was to basically kind of try to guess if the coin is biased or not. So I said that one way could be defining a bare minimum threshold of probability of heads or tails.
I think, okay, so I think the communication gap was an unbiased coin has exactly 0.5 probability. So all events are equally likely for an unbiased coin, which means
so basically the number of coins in the distribution, so heads in distribution. So for example, 101010 will have 3 ones and 3 zeros. So probability of heads in that particular event is 0.5. But in this case, you just had more zeros, say 8 zeros and 2 ones. So that means out of 10 coin flips, 2 were heads and 8 were tails. So that basically gives the probability of heads to 0.2, which is at our threshold. So say it was just one head and everything is tails, so that is less than 0.2. Hence, it is an alarm bell. Like that was one intuition.
Cool. So let's do this. If I keep the probability, what do I want to say? I want to highlight the difference between this. So you said some very important things. So you said if I see 1 0 1 0 1 0, then this means that the probability of heads is equal to 0.5, because about 3 out of 6 are heads, and so the probability of tails is also equal to 0.5. Is this correct?
Yes.
Cool. This is a good way to start guessing what is the if the coin is biased or unbiased. And what you did was essentially you tried to think in your head about, oh, if the coin was unbiased. Let's not get into that. Before we even get into that, can you tell me if I put the I want to get into two approaches of estimating probabilities. What you did exactly was counting. Counting is the frequentest approach to probability estimation. So if I see out of 30 flips, if I see 20 flips heads, then I will say heads are twice as likely as tails, because 20 heads, 10 tails. So 2 times as many heads as there are tails, which is essentially counting. Is this fair? Do you buy this?
Yes.
The other approach to this is you try to think of, like, in general, coins are unbiased. If you tell me nothing and you give me a coin, my natural assumption will be this is unbiased. Or because I know nothing about this, I will be forced to assume it is unbiased. Is this a fair start?
True.
Now, if you start looking at coin flips and you see only heads, your first flip is heads, you will start to think, okay, this gave me the first flip heads. This is probably, I need at least one more flip to determine if there are more heads than tails. But so far, heads seems to be the likely outcome. Your second flip is heads. You will probably start thinking, and complete my statement here. What are you going to start thinking if you're doing the counting based approach?
Maybe it gives more support that it is unbiased, unless like we should define some number of trials which we need to do in order to consider the threshold condition, and after that we could just like, first thing is we should define some number of trials for which the threshold condition should be valid.
What is that number of trials? If I tell you there
That
are,
is random, I guess, like at least 20, at least 50, 100, whatever.
Are we getting the
then
t values here?
if I give you something like this, is counting going to say, what is counting going to tell you is the probability of tails?
that would be 0, but this is I won't say that the
But
probability.
yeah, go ahead.
Yeah, I get your point.
So this is the frequentist approach is not wrong. It is perfectly valid and it's used a lot. So it's clearly like possible. The only challenge is when your data are incomplete or there is no such number that you can place on the trials that will exactly give you the probability of tails. Because if you only see heads, your probability of tails will naturally be 0 if you're only counting. But logically, you know that there is a coin, even if it is extremely biased towards heads, there is some probability of tails. Like at some point it can flip. Is this fair? Do people understand this argument?
Yeah.
And
Yeah.
that, sorry, go ahead.
No, I follow the argument. Got it.
And that is essentially the difference between frequentist and Bayesian methods of thinking. Like the Bayesian starts, if you know nothing, you place a uniform prior over every possible outcome, which means every possible outcome is equally possible. So if there are infinite outcomes, then everything will have a very, very low probability, but it will have a probability such that it sums to 1. Right? If there are 2 outcomes, then they will have 0.5 probability. If there are 5 outcomes, they will have 0.2 probability. Because as a Bayesian, you don't know anything, which means everything is possible. As a frequentist, you might start observing some data and you're like, oh, this outcome is more possible, more possible, more possible, more possible. But then if you don't see any other outcomes, you have no idea what probabilities to place on those. And then you might jump into the other approach, which says, okay, then if like what I might set some threshold for this heads. If I see like an infinite number of heads is probably 0.999. And then the rest you will divide among all the possible other outcomes, which in this case is only tails. But that again, you have set arbitrarily. So in this tutorial, I'm going to focus on the other approach, which is Bayesian statistics, where you start by knowing nothing about a coin, which means heads and tails are equally likely. So the minute you observe a certain heads, your probability, your bias towards heads goes up, which means you think heads are more likely. And if you observe more and more heads, you increase that bias, but you started at 0.5. So you can only get to a certain point. You will still have some finite probability of tails. Let's say, again, this is completely arbitrary. Let's say every time you see a heads, you say heads is twice as likely, right? So even if you divide the probability of tails by 2, that's not the right way to express it. Let me not confuse you with that. Hopefully I've been clear so far about like the difference between frequentist, which is a empirical estimation or counting, and the Bayesian way, which is like place a prior, assume everything is equally likely, then change the probabilities as you see the data. And this is what I will try to capture in code. Let's do this on a separate line. So What do I want to do now? Now I want to define some, suppose I see some data. Okay. Let's generate some data. Actually, let's set a flipper is I want to generate 10 samples with a certain probability, which is 0.7, let's say. And this is my observed data. Let's rewrite this observations. Now suppose, so this is the world in the world, or let's say this is Swapneel's world. And I give this data to Unicode Research, gets observations. And all Unicode Research can do is see that, oh, this is the observation that Swapneel gave me. Now Swapneel knows what his world is, and Swapneel is saying, Unicode, can you actually recover this world for me? Can you tell me what my world is like? And the best thing Unicode Research can do is, okay, let's build a certain model that could have produced this data. And so because Unicode Research knows nothing else about the data, they have to start with the assumption that the coin is probably unbiased, and then recover what the true bias might be like, or if the coin is truly unbiased, then recover that. And so this now we're jumping into probabilistic programming. So now you define a certain model for the world. You don't know the true world. Only Swapneel knows the true world. I feel very weird calling myself names in third person. Let's say this is Jay's world. I don't want it to be my world. Cool. And so what we want to do is recover Jay's world. So first we build a model for Jay's world. We say that this model, the way this model works is there is probably some bias, and now we get into Pyro syntax, pyro.sample. I should write import Pyro. Okay, let's add a bunch of imports on top. Import Pyro. What else will I need? I will need Pyro.opt-in. And I will need this functions for so the first thing I want to do is I want to sample a certain coin bias. Now bear in mind that I don't know what this coin bias is. So what I want to start with is a uniform distribution over 0 and 1. But because this takes a certain format, I should write th dot tensor 0, and I should write th dot tensor 1. Th is just torch. I abbreviate it so that I don't have to type as much, but you can do it as you like. So again, to be very clear, like what this does, if you just run this function, it will basically just give you a sample, but because it's pyro.sample, instead of just sampling from the torch distribution, it will also log this. So do I, how did I don't remember how to show this. but there is this gets logged. Trust me that this gets logged somewhere, and Pyro knows that you're sampling. The reason Pyro needs to know what you're sampling is because it builds this sequence of like how samples occur, and then I'll get to the inference part after this. But basically, it's the same sampling with a different syntax that is specific to Pyro. So I have sampled a certain value, and to be clear, if I rerun this, it will give me different samples from the uniform distribution, ranging from 0 to 1. Cool. Everyone okay so far? Again, to reiterate what I am doing, I'm building I'm building Unicode's model of Jazz World. I don't know what Jazz World is really like, but I know that a probability for a coin has to range from 0 to 1. So I'm placing a uniform distribution on top of it, which means every single value has an equal probability. It could be any of these things, the coin bias. And then what I'm doing is I am sampling a bunch of coin flips from it. So if I say I in range n, or n is what? N is length of data, right? N is equal to length of data. Length of data is number of coin flips. At any point, please interrupt me. I'm in a zone writing code, which is not a good thing, but coin flip is equal to, and can someone following this syntax, can you tell me what I should write in this line? Now I'm trying to sample a coin flip. Remember that before, the way we did this, and I don't want this to be Jaydeep or Jagrut. I want it to be more people to answer. The way we did this before was we sampled a coin flip from a Bernoulli distribution. Now following the same thing, could you tell me the syntax and the what I should write here? Anyone new? You can guess, you can be wrong. I mean, I have guessed and I have been wrong in an interview before about this exact statement. So I don't think it gets worse than that. And I was supposed to be the expert in this area. So yeah, this has been, this was as of a month ago. So don't worry about being wrong. Just try and figure out like what is the syntax for coin flip, given that this is the syntax for sampling a random variable from a uniform distribution. And you know that a coin flip is sampled as a random variable from Bernoulli distribution. Anyone?
So the same Pyro dot sample line but with this dot Bernoulli, or
What should be the first keyword, first argument?
coin bias again, right?
So right now you're sampling a flip, right? You're not sampling the bias. So the reason, and maybe I should have been clear about this before, but now this is a flip, and we're sampling multiple flips. So yeah, I should have probably been clear about this before. Every new random sample has to have a different name, which is why I'm adding this IE here. But you are right that this has to be this.Bernoulli. Can you tell me the parameter for this Bernoulli? Bernoulli. There is something that goes here, right?
This will be n as well, right? So n, I suppose, and yeah, 0 to 1 and n.
So let me give you one chance to look up what we did before. This is what we did before. We defined a certain probability, and then we defined a distribution with the parameter as.
And then sample with size.
And then we sampled with size, right? So here, what you want the parameter to be is There are two possible answers. You gave me one of them. I'm asking you again. So it has to be the other one. What is the other one?
Yeah, I'm not sure. th.tensor 1 directly we can put it there, I suppose.
Right. So I should explain again, like what so the Bernoulli distribution takes the I can probably shift tab. This is excellent. So it takes an argument as the probabilities, which is what I was saying. So because we don't know what J's model is like, we have kept a random probability, and this random probability is what will be the coin bias that we will sample from. Do you follow?
Yeah. Yeah.
I don't know if it might be easier to write it down. So we think there is a certain bias.
Yeah.
We don't know the bias. So randomly sample a bias, and then using that bias, create a distribution. And then sample coin flips from distribution. Is this fair?
Yeah. Got it.
Again, like I am clearly not doing a great job of explaining this. So at any point, if there are questions, please pause me and let's get back to this.
No, I think I get it. So we'll be updating the bias iteratively too, right? Yeah.
Exactly. So now that we have defined a process where we randomly sample a bias, using that bias create a distribution, sample coin flips from that distribution. Now the last thing to do is compare coin flips.
Swapneel,
yeah.
I had a doubt. So basically, if we see, right, as like when we started, we said, right, we start with, let's say, equal probability, right, sort of 0.5 right now, right? But as we are sampling from this distribution, right, so values are very, like, they are within uniform distribution of 0 and 1, but they are not 0.5 exactly right now, right? So like the belief is different, right, at each particular sampling point. Where it should have been 0.5, right? If we, let's say, we start with equal outcome, like belief, and then we update based on as we keep on seeing the trials, right? Or like, could you clarify a bit more on that?
Yep. No, you're perfectly right.
So like in this case, when we're sampling from uniform distribution, but here the probability value is like changing, right? So it's not exactly 0.5 right now, right? So how does that changes the outcome?
So what I'm saying here is your assumption as a Bayesian person on seeing a series of coin flips and knowing nothing about them should be that the bias can be anything. The bias,
it would be anything, right? Basically, like we have some starting point, right? So where we give equal importance to all, unless and until we have some specific details, right?
I guess this is the case where we could assume it's not a coin, it's some object that we've never seen before. And if it flips, we don't know the outcomes beforehand, right? And that's why we are just going with the bias that we see.
You are right. I'm trying to find a middle ground between. There has to be a simpler explanation than the one I'm thinking of, which is like involving terms like the support, which I don't want to get into right now. In order for the coin bias to be a random variable, I still need to give it a space of outcomes over which it can take values. Is this correct? Like, not is this correct? Do you buy that?
Yeah.
Like, I know that the starting point for coin bias might be 0.5 if I had seen no data. But now that I have seen data, I know that it can take a range of values,
Yeah.
right? And I want to find the correct value over this range of values, which might as well be 0.5. It could be 0.5, but it could be a bunch of other values. Is this correct?
Yeah. Yeah, that's
So
true.
all I'm doing is I'm giving it this space of possible values over which I want to find the right value.
Okay. So like, you are basically defining your hypothesis space, and in that space, then you are like basically performing, let's say, trials and searching out right what the exact bias is.
Exactly.
Okay.
And the reason I wasn't getting into initialization in this piece of code is because it gets too complicated, but there is a way that you can initialize it to a certain point and then start around searching, which is, I
Okay.
think, what you were asking, where like, shouldn't we assume 0.5 to begin with? Yes, we should.
Yeah.
And there is an initialization scheme for doing that, but right now I don't want to get into that.
Okay.
Just because it involves a specific function that you have to then provide and go on. Anyway. But you are right. You are not wrong. This is perfect. That the question you raised was perfect. That if we know nothing, shouldn't we assume 0.5? Yes, we should.
Yeah.
I am just jumping past that point and giving it a space of outcomes to search over.
Okay. Yeah. Now it's clear.
Why should we assume 0.5 though? I thought like.
So if you have a coin, someone gives you, and you have nothing else that you know about, right? Right now, we have not looked at the outcomes, right? Someone gave us some data set. Yeah, sorry.
But suppose we don't even, suppose it's not even a coin, it's some random object where we don't know how it could even flip, right? And what probability distribution it could flip. We have no prior knowledge about that. So we shouldn't assume anything, right?
Which is exactly what we're doing by saying place a uniform distribution over the space of all outcomes. Okay. So we know that the coin bias can take any value from 0 to 1, right? Which is the probability.
Right.
Of flipping heads or tails. And that's what we're doing, is saying place a uniform probability over all possible values from 0 to 1.
Right, but then when we come to the question of we can initialize it, so I'm not sure how or why we would initialize.
So there is an the reason you might initialize it to 0.5 is because you hold this belief that heads are equally likely as tails. So you're saying start the search at 0.5. You can start the search elsewhere also. There is nothing against that.
Okay, got it then. Yeah.
Cool. Where was I? Yeah. So now the model, I think, of the world, my model of Jazz world, or Unicode's model of Jazz world, is that there is a certain probability or there's a certain coin bias, and then using that bias you have sampled 10 coin flips or n coin flips, whatever n may be, which is the length of the data provided. And that's it. That's all you have to do to write a model. And the second thing you need is a guide, which is a Pyro specific thing. So now, what do I want to say about this? The way you do inference is you say that there is some distribution. So you specified the range of values that this can take. But now what you are doing is saying that this is, what's the right way to explain this? Because we haven't gotten into variational inference, so I don't know how to explain models and guides without that. The reason what I'm thinking of is how to abstract away like a semester's worth of math so that you don't have to study variational inference, but you can start to understand how there is this search that is going on over the space of coin bias. So let's say you have placed, I don't know if I want to get into the concept of priors. How many of you are familiar, by a show of hands or comments, of the concept of priors and posteriors? Okay, so some of you, not all of you. So let's get into this idea where, so we said, to give you a brief intro to a prior, when you don't know about what happens when you don't know what value a random variable takes. What we discussed was place a distribution, flat distribution over it. When I say flat, I mean all possible values have equal probability. Yeah, I mean, I could have done this before also. For now, is this English explanation clear? Like a flat distribution over it, which means all possible values have equal probability. To be clear, I know the outcome space. I know what values it can take. I just don't know which value is more probable, which value is less probable. For instance, the food you have at home, like, there is a finite set of outcomes like this. These are the 15 items I have. It's just that some items I have on a daily basis, some items I don't. And some items I have very, 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 very occasionally. So I don't know the probability, but I know the set of outcomes. And by placing a flat distribution on top of it, you're saying everything is equally possible to start with. Then as the days progress, I will see what food I eat and I will update probabilities accordingly. Do you understand this much? Or let me be clear, is that, like, do you buy that? Sorry, I should have been clear. Oops. If you buy that, then what I'm trying to go for is just this distribution is called a prior. A prior is just a distribution that you place on a random variable when you don't know anything about it. And that's exactly what I'm doing. I said that the space of values for the coin bias is uniform, but I don't know the probability of each value. So how do I, again, like, how do I go about this? I want to understand what possible coin biases could have produced this data. And in order to do that, I have to change the values of coin biases. And I will change the values and compare. Yeah, I think this is the right way to go about it. So taking a specific example, for coin bias, I do not know what value to start at. So place a sample from uniform distribution. This is my initialization. But what could be possible distribution of coin bias? Which means a distribution is telling you what values it takes with what probability. In a frequentist way, counting is what Jagrut did to find coin bias, or let's say to estimate coin bias. But failure case, if you see all heads, counting will not tell you what the coin bias is correctly, because it will tell you the probability of tails is 0. Is everyone following what I've said so far? Or any question about this so far? Especially Gaurang and Devang, I'm basically trying to get to the concept of priors by explaining this specific example. So if you don't follow, please tell me.
Got it till here.
Okay. So coin bias, we don't know what value to start at. So we started by just sampling a random number from all possible random numbers that it can take. Then we said, okay, but what could be the possible probability distribution? When I say distribution, I mean probability distribution over coin bias. That is what values it can take with what probability. In order to do that, that gets back to Jay's point about, okay, we need to start with some assumption of like heads is equally probable as tails. No, I don't want to get to that yet. Initially, I don't want to get to that right now. For frequent discounting, if we start by counting, then we run into the problem of if the data is a bad sample, then it will tell us that probability of tails is 0, which is clearly untrue because a coin can always flip tails with very low probability, but some probability. So what we do is place a prior distribution, uninformative prior. So, or flat in this sense is again a flat probability distribution, means all outcomes are equally likely, which is uninformative because it doesn't tell you which outcome is more likely than the other. I will pause in case you have questions on flat priors, uninformative distributions. Prior also means before, so this is all before you see any data. So what you start with, okay, assuming that is true, assuming you understand what that means, I will place a prior distribution that I will learn. So this is now learning will happen here about like what distribution is the coin bias, what values that I will learn, or this answers the question, what is the value of coin bias likely to be? Okay, is this line clear? Like start with the prior distribution, learn something, so that let's start with the flat prior, hopefully learn something that will tell you what is the value of coin bias likely to be. Is this statement clear to especially Gaurang and Devang?
Yep.
That is exactly what this is called, prior distribution. And this learning will lead us to a posterior distribution. So, and I will get to like an example with both of these things, but these are just like distributions before and after seeing the data. So the prior is learned, or the parameters for the prior are updated to learn the parameters for the posterior distribution. Posterior also means after. Learning happens from data. So this is exactly what like inference is all about. There is a certain prior placed, you use data to update what you see and learn some sort of posterior. Okay. In order to do this, for probabilistic programming, you need to place this prior on the parameter, and then you need to get the posterior out, right? So in order, the way you place this prior is using this function that is called a guide function. Write this here. F flipper guide, which has the same call signature as the model. So it takes in the same parameter, except now what guide does is I define P, which is my coin bias. So I'm placing a prior on top of coin bias, which sampled from a distribution called beta. I will get into a minute into what this distribution is, which takes two parameters, A and B. Now getting to what beta distribution is. So how do I do this? Fine. Beta is equal to beta dist is equal to dist. This is confusing. B1 M is equal to dist dot beta what I'm doing is showing you what this beta distribution is. And if I just set 1 1, this is m dot sample. Shit. What this does is it gives me a bunch of random samples which are uniformly distributed between 0 and 1. But the beta distribution, this is actually a special case of the beta distribution, which can actually take a bunch of other values. So this A and B that I'm setting, varying these A and B can give you all of these different colored lines. So it is more expressive. It can take on different value. And the reason that we use this instead of just directly using a uniform is because the uniform distribution you can't change the values of the uniform. Like you can't make one value more probable than the other. Like a uniform is a flat distribution, right? The beta can be flat or it can be beyond flat, like it can take some values more than the others. And because this learning step might tell us that the coin is very biased, we need to be able to allow for that to happen, which means the distribution has to be flexible enough to be able to model that, which is why we switch into like a more flexible prior. Do you understand what I mean? Like we start flat, but we have to be able to learn something. If we don't allow learning to happen, then learning can't happen, which means we need a distribution that can, with parameters being changed, that can learn something sharper. Or in this case, for this black, it is saying 0.2 has more probability than the other values, which means a coin bias is more likely to be 0.2 than the other values, which means we can learn 0.2 as a value because that can be represented by the distribution. However, if it cannot be represented in the first place, then there is no point in doing learning. So far, do you follow what I'm saying?
Yeah.
This is like a lot to digest. So like, feel free to tell me if you missed something, if you want me to repeat something, those kinds of things. Okay, cool. So we've been through like why we need a flexible priors. Now let's get to like starting point for A. The same thing. Pyro.param. So now we're not sampling A. We are just defining a starting point for A. Beta A we want to sample from torch. Hence, just copy and paste this. We don't want to sample from, sorry. We want to set this value to torch.tensor. And for reasons that will remain undiscussed in this lecture, we want this to be dot positive, which is what we are placing a restriction on the search space. That's all we're doing. And for B, we are doing the same thing. So these A and B might change. Like we said, we've defined a starting point for beta A and beta B, which gives us a uniform prior. But because of learning, that prior can be changed into a sharper distribution. So that can tell us the values of what the coin bias, what values of coin bias are more likely than the other values, which is what learning is defined as. Okay, cool. The last thing we want to do is we want to tell this model to actually use the observations. So when you get this data, you actually want to tell it to use this data to condition what it can see. Now, what does conditioning mean? It basically means the same thing you were doing mentally when you said if data is equal to 1, 1, 1, 1, 1, 1. Every time you see a 1, you are thinking, oh, heads is more likely, heads is more likely, heads is more likely. You're telling the model to do the same thing where each time it sees a certain data point, it updates this parameter for this distribution to such that your coin flip actually matches your data. I will pause here and I will slowly repeat what I said. Every time it sees this observed data, it tries to update this parameter, the parameter P of this distribution Bernoulli, to match this coin flip to what was actually observed at that point in time. So each time it sees a 1, it will try to increase probability of 1 such that you actually end up generating 1. With the point being that I want to change my version of the world to reflect what Jay's world produced so that hopefully the worlds can match. Everyone on board so far? Cool. Awesome. Okay. With that, we're actually done with the coding up for this. So again, to reiterate what we have done, we set a certain coin bias as the probability of flipping heads, and we sampled a bunch of coin flips with that probability. Then we placed a prior over this coin flip that says, okay, I want to start flat, but I want this to possibly learn something meaningful that can tell me the coin might be, if the coin might be biased. And then we finally told it to use the observed data to condition this bias and produce coin flips that actually resemble the data that we saw. That's all we've done so far, and that's all you need in order to do inference. Let's get to inference. And now this part might be a little tricky to follow, but it is a sort of learning procedure called variational inference that I can request Akash to give us a lecture again, but generally what we're doing is you're taking, this is almost impossible to like fully explain, but the bottom line being it's a gradient based learning approach that gets you to a point where your generated data starts to resemble your observed data. That's all I want to say about this. There is a certain optimizer involved. There are certain loss like steps involved. And I think that's all. So let's go through it one by one. The first thing is you set a learning rate and you set, again, these are certain optimizer parameters. you define an optimizer using these parameters. Because why is an optimizer necessary? You're doing gradient based learning. It's more or less the same. This is PyTorch stuff. Then what you're doing is you're defining a loss sort of model, a loss function that says, I will take the model, I will take the guide. Remember that the guide was our approximation. So we think this is our approximation to how this is produced, right? I should not say, right, that was the bad. Our model is our approximation to the true world. A guide is what we learn, the prior that we place on the model. But yeah, we give it the optimizer and we give it a certain loss function. So yeah, this is hard to actually boil down unless like you watch separate videos on variational inference. But other than that, like let's reduce the number of steps here to say 1000. And at each step, this is like your for your epochs, you iterate over the observations. This is just printing. Let's do we can do printing. And at each after every 100 iterations of learning the values of beta A and beta B, which remember is how we learn this coin bias. Let me print the value of let me do this. The reason what I'm basically printing is the value of coin bias. So don't worry about like what this looks like. This is actually the value of coin bias is equal to A upon A plus B, which is the mean of the distribution, mean of the learned beta distribution. So it's the same as saying the what is it the same as saying? Mean of the uniform distribution. Is that easier to explain? I think it should be, right? I think it should be. Can someone tell me the mean of the uniform distribution? Can someone tell me if I tell you there is a uniform distribution over 0 to 1, what is the mean value of this distribution? Is that the right way to approach this?
0.5, right? If it's 0 to 1.
Yes. What I was thinking of. I think, yeah, I think that's the right approach. Mean of the, yeah, you're right. Mean of the uniform distribution is 0.5. How did you get to this 0.5?
Like upper bound plus lower bound divided by 2.
Equal to upper bound, let's say 0 plus 1 divided by 2, right? If the reason I wanted to do something visual, that's why I was a little confused. Let's say, I don't know if I've imported Python. .py plot as plt, and I want to do plt.hist of and p dot random and okay, cool. Cool. Can someone tell me the mean of this distribution?
Probably 0.
So what you basically did was you took the peak of this problem. So this is
Yeah.
probability distribution. Well, no, this is not a. I should have normalized this.
This is a normal distribution, right?
This is a normal distribution because numpy samples a random normal variable. I don't know if there is a normalize equal to true here.
So
Density.
like what do you want, like uniform?
Now this is a probability distribution. So the reason I was saying that before it wasn't a probability distribution is because this y-axis is not a probability. You understand? 350
Yeah.
is not a probability.
Yeah.
So that's why I was going for this.
Yeah.
So now this 0.4 is actually a probability. So you're saying at somewhere around 0, roughly the probability is 0.4. And the same way, now if I want to sample a beta, a random variable that is m is equal to dist dot beta. Yeah, I should do this. Let's do this. M is equal to dist dot beta. Pyro dot param beta a. Let's not do this. X is equal to m dot sample dot size 1000 and I want to do plt dot hist. So oh shit. Give me 1 minute, I'll be right back. The reason I'm doing this is I want you to understand what happens at each stage of this learning, like what is changing, how things are changing, and what is learning doing to these parameters, this prior distribution that we started out at, which is why I'm plotting all of this at each series of iterations so you can see how this distribution is changing. Cool. M dot sample torch dot size 10,000, and now I want to plot these samples. TMP is equal to plot dot histogram. Hopefully this is the same thing and this will work. Yikes. Flipper model. Did we not write flipper model? Do not run it. Obs is not defined. What were our observations? Obs was actually our observations. What? We not run anything? Thought we did. Or we want, let's say, 100 observations, 0.7. I don't want to actually. Fine. Flipper model data. Why is this not tab? This is not tab. This should have tab completed, but for some weird reason it is not. Unexpected keyword constraints. What got an unexpected keyword? Model trace. Pyro.param. Constraint should have been keyword. Yikes. Type object is not subscriptable. What did I miss? What did I miss indeed? Th.size. Let's do at least. Dot item. Think dot item. And this is should be beta B. Ugh. Dot value. Why is this? Is not subscriptable. A is equal to pyro.param beta A, B is equal to pyro.param beta B, and B. I'm missing something. What am I missing?
It is showing that you need to index it.
Shit. Shit. This was so stupid. This one was missing a bracket. Okay. So, oops. I should have. X. Okay, hopefully this will run now. Why is this so slow? Really slow. Maybe I should take less samples. This is really slow. Bins is equal to, let's say, 30. Is this? I mean, it's working. It's just, I'd really imagine this would be faster than this. So slap 200, 500, at least 2 plots. Can't imagine why this is working so slow. Kernel crashed. Wonderful. Maybe I should just append samples and then okay, yeah, this is really bad. I do need more samples, but okay, let's stop the notebook. X is equal to x dot append. No, I think x dot append does it in place. Yeah, this is right. I was thinking about pandas. And I do want to print this though. Oops, later on all. Oops. Okay, cool. It is going very slowly, but it is progressing. So you see that you're learning, if you're printing the mean value or the mean value, which is the coin bias, it is starting to learn the coin bias slowly and progressing there on out. Because it sees data that is, and now we have to go back and see the true bias was 0.7. So you want to recover something like this, right? Because this is what generated the observations. So we would hope that our learning procedure is leading us to this coin bias. And I'm plotting the coin bias at each point and it's going slowly towards the right range, but I need to increase the number of iterations that it is running. And probably play around with learning rate and all of those things, which is typical machine learning-esque hyperparameter optimization. But you see the point, hopefully, that I'm going for, that you start out somewhere and then you increase your bias to a point where like things are starting to be equal. Do people buy this? Or I should pause and say, okay, here is the point where you should ask me questions. Like, what did we get out of this? That is one question I would ask you, if anyone wants to answer that. Can someone summarize like what? Oh, yeah, I see a hand raised, please. Go ahead, if I missed that. Oh, I think you accidentally raised your hand then, Shway. Let me know.
Sorry, I've been raising for a while.
Cool, gotcha.
Not for this. Not for this.
So, and I will share this entire notebook with you all so that you can spend time reading through this and like what is going on here. And let's actually. This was, okay, let's see what X was. Oops.
X is a list.
Yeah, and so there are 10, we are printing it 10 times, right? So do I want, fuck it, let's do it. Will this work? I was afraid of this. This could potentially be kernel crashing. Although it's just 10 histograms, right? plt.show should show me 10 histograms one after the other. Weird that beta distribution takes so long to plot. I just want to show you what sequentially what the distributional updates are looking like. Like we see that this thing is updating, but why do we think this, like what does this mean in terms of the distribution? So the values of beta A and beta B are changing, which means that this, I don't know why this is not working or why this is just taking so long. Maybe I should reduce the bins. Or maybe just stupidly, maybe I should remove density is equal to true, or at least get to a point where I'm plotting stuff. Because I've plotted stuff like this before. It's not optimal, but it works. Very weird. Should I not add plt.show until the end? Why? Why does the first plot itself take so long? Is 10,000 values that big? Evidently. Clearly, I'm doing something wrong with plotting, so the plots are not working. But if you can get this to work, please feel free. Anyway, this was it for today. So what we saw was you can actually learn a sort of coin bias from the observations that you saw, using this ability to perform inference. Are there any questions? And of course, please go through the notebook. But what I'm getting at is, for the social media stuff, we have built this sort of simulator that can give us these nice plots. Where is this? Okay, clearly haven't run this notebook either. We've seen that we can simulate a graph, we can simulate tweets from these people, we can simulate their interactions. Now the question is, if we have some tweets, can we actually learn what these colors or what these beliefs were like? Were they right wing? Were they left wing? Which in this case corresponds to pineapple pizza haters and pineapple pizza lovers. So based on their tweets, which indicate a certain stance or on pineapple pizza, can we learn back what their beliefs, based on their tweets, can we learn back the beliefs? So it's like belief to tweet and tweet to belief. That's the forward and inverse process. The same way that we did a coin bias to flips and flips to coin bias. That was the point of like this entire exercise, that in order to get to this point, we need to understand the very simple case of coin flips and then how learning happens in that case. So hopefully I have conveyed like a tiny example for doing this kind of stuff. And I'm always available to answer questions about this. I will also drop this notebook in chat so that you can go through this and understand what this stuff is. What I will say, you need to study what stochastic variational inference is. And I'm happy to spend a couple of sessions on studying this with you. But let me know what you feel about this tutorial, and then we can pick up from there. Any questions, comments?
I just wanted to, so for like guide model, you like the function that we have written, and that just will like define the parameters, that's it, right? Or like basically is there anything else as well? Because it takes data as the input, right?
So guide takes data because it follows the same signature as model. But as you can see, the model is really what we are conditioning on the data. The guide is there as an approximation to what we feel the model looks like. To what we, guide is there. I should explain this better. This is bad.
So it is like, if I get this thing correct, so it's like we have some true distribution. We are assuming some like another distribution, let's say that we are starting, and we're trying to approximate that, like whatever distribution that we started with, like closer to what the observational distribution of data might be, right? Similar to like VI, if we think of that. So where we start with the approximate distribution, right?
Exactly that. And this is called our variational family.
Okay.
So So we have some true model of the world. We are approximating it with our own model. The guide helps us do that. That's all.
Okay.
We don't know how the world produced it. We don't know how the true data was produced. So we are trying to approximate the data generating process and then match the data sets that we have produced with the data sets that the world actually produced. As long as we can get the same data out, the claim is that, oh, we might have a good shot at like, this is actually how the world works. Now, of course, the argument against this is, well, what if you did 3 things wrong and they all canceled each other out and you ended up generating the right data? That can always be like an argument.
Yeah.
But yeah, at least like you're doing something. The claim is at least you might be doing something right.
Yeah, got it.
So yeah, I'll stop there for the day. Other questions, more like fundamental questions about like coins and flips and probabilities and distributions and stuff like that. Is the concept of prior and posterior, like this starting point and ending point for the mean of this distribution, clear to Gaurang and Devang at least?
Yeah, got it.
Yes.
I will say that terminology is painful to get familiar with, but once you're familiar with it becomes very nice to get into the literature. Anyway, if there are no other questions, then I can stop recording.